Hello, my name is Nurfatiha Fatana Khawla binti Asidi, and today we will discuss about one of the phenomena in quantum mechanics, which is the quantum tunneling. So what is quantum tunneling? Quantum tunneling is a phenomenon where a particle can penetrate through a potential energy barrier that is higher in energy than the kinetic energy of the particle itself. So we can see the illustration from the figure below. What happens is that when the particles reach a barrier that they cannot overcome, a particle's wave functions changes from sinusoidal to exponentially diminishing in form. For example, the solution for the Schrödinger equation in the figure below is as stated below, as stated beside. Then, what is a transistor? A transistor is a type of semiconductor that can conduct and insulate electric current and voltage. The transistor was invented at Bell Laboratories in 1947, and it can act as a switch and amplifier. Simply put, a transistor is a miniature device used to control and regulate the flow of electric signals. Combining transistors can form a logic gate, and computer logic gates can make simple decisions using Boolean algebra. These techniques are the foundation of modern-day computing. Moreover, the transistor plays an important role in amplifying electronic signals. For instance, in FM receivers, where the received electrical signal may be weak due to disturbances, the transistor is needed to amplify the signals and provide audible output. So now we already have the fundamental information about quantum tunneling and transistor. So let's dive more into the topic.
Hello, I'm Marcel Judith Paul. In this part, we discuss about the quantum tunneling in nature and technologies. So a brief explanation about the quantum tunneling. It is a fundamental quantum mechanical phenomenon where a particle can pass through a potential barrier that is classically shouldn't be able to surmount due to insufficient energy. So this phenomenon has significant implications in both nature and also in technology. So next we look at the quantum tunneling in nature, which is the nuclear fusion in the sun, where we know it is very common thing that happen naturally. So how does it happen? So in the core of the sun, temperature and also pressure are incredibly high, which it creates conditions where hydrogen nuclei, which is the proton, can come close enough for the strong nuclear force to overcome their electrostatic repulsion and fuse together, which is to form helium and release vast amount of energy. So usually the proton's kinetic energy is insufficient to break through the Coulomb barrier even at the very high temperature. Coulomb barrier is the electrostatic repulsion between the positively charged nuclei. And it should be noted that heavy ion fission reactions are not the only tunneling. Even in nuclear physics, there's also a lot of things that can happen in naturally, such as alpha decay, fission, various ray decays, and also nuclear structure from. Next, we look at the technological applications of quantum tunneling, which is the scanning tunneling microscope and the flash memory. First, we look at the scanning tunneling microscope, which is it uses the concept of quantum tunneling to image surfaces at the atomic level. In this case, a sharp metal tip is brought extremely close to the surface to be imaged, and a voltage is applied. So in tunneling current, the electrons tunnel between the tip and the surface. When the tip is close enough, it creates a tunneling current that varies with the distance between the tip and the surface. So how does it work? By scanning the tip across the surface and measuring the tunneling current, a highly detailed map of the surface's atomic structure can be obtained. So this technology is essential for nanotechnologies and material science research. Next, we move to the flash memory, which is it stores data using the floating gate transistors, which rely on the ability to store charge. So, quantum tunneling in erasing data. When a high voltage is applied, electrons can tunnel through the thin oxide layer to or from the floating gate, with each allowed data to be written or to be erased. So I can say that quantum tunneling is a key concept in both natural processes and technological advancement. In nature, it enables nuclear fusion in stars, like the sun, while in technology, it is utilized in devices like the scanning tunneling microscope and flash memory. So this application highlights the profound impact of quantum mechanics on both of our understanding of the universe and the development of cutting-edge technologies.
So today I'm going to talk about introduction and evolution of transistors. Transistors are miniature semiconductors that not only generate and amplify electric signal, but also function as switch or gates, controlling the flow of current or voltage. It is also made up of three semiconductor metal layers, each of which can carry current that confined by quantum physics to specific discrete energy level. Transistors function as amplifier, form small input of current into larger output. While switch, it can be in one of two states, either on or off. Next, in evolution, there are 5 flows. First discovery. The discovery was made on December 23, 1947. Walter Bardeen, John Bardeen, and William Shockley shared the 1947 Nobel Prize in Physics. In some ways, the discovery of transistor at that time was the work of one individual, which is Marvin Kelly. The first transistor radio that exists. It happened shortly before Britain. Bardeen Shockley were awarded the Nobel Prize. The first major application of the transistor had emerged. This was a small portable radio that was even called a transistor after the component that made it possible. Texas Instruments, which was the first company to introduce a radio of this type. So for the third, which is the invention of bipolar junction transistor, William Shockley made a successful attempt of making this BJT. William Shockley, John Walter, and Bardeen awarded with the Nobel Prize for this achievement in 1956 for field effect transistor (FET). The first attempt to make FET was made by Julius Hager in 1925, and sadly he failed miserably, but he was lucky enough to get the concept patent. In 1945, the junction FET was the first device to be constructed by Heinrich Walker. Fifth law, which is the last, is miniaturization about BJT until miniaturization. For BJT, it consists of two transistors, which is PNP and also NPN. Each transistor consists of three terminals, which is emitter, collector, base. For PNP, as you can see in the picture, the current from the battery is flow in from the emitter and then will flow out through base and collector. While in NPN, the current from the battery is flow in from the collector and also base, and then will be flow out from the transistor through emitter. I also put the type of BJT is FET, field effect transistor. It consists of two types, which is P channel and N channel. Each channel consists of three terminals, which is drain, source, and gate. Current can be controlled by varying the voltage at the gate. As you can see in the picture, N channel, when we apply the reverse bias in V gate source, the depletion layer will form where the P-type and N-type region meet. This required gate source voltage to be less than the drain source voltage. The more biased it becomes, the more depletion region to grow. The higher the difference between gate source and drain source voltage, the greater the depletion region, and cause smaller current flow. In P channel, as you can see in the picture, the gate source voltage connected to the positive rather than negative, and the gate source voltage needed to be higher than the drain source voltage. If used the forward bias in N channel FET, the component will low since it cannot handle any significant amount of current. Last part, miniaturization. In electrical devices, miniaturization refers to fitting more transistor node onto a smaller integrated circuit (IC). Moore's law is an observation that the number of transistors in the chip doubles every 2 years or so. The law also states as the number of transistors increases, the cost per transistor falls.
Hello everyone, my name is Munira Anastasia binti Muhammad Hatta. In this part, I will explain about quantum tunneling in transistor. Quantum tunneling in transistors is a process that allows electrons to pass through barriers that would typically stop them under classical physics, becoming particularly significant in the realm of small-scale transistors. Next, tunneling becomes significant in small-scale transistors due to the physical limitation brought on by miniaturization in the basic ideas of quantum physics. Electrons have few obstacles to cross in order to carry electricity when transistors are sized down to nanometers. This decrease in barrier thickness raises the possibility of quantum tunneling, in which electrons are able to flow through barriers that would be impenetrable in normal circumstances. Now let's talk about how tunneling becomes the reason of leakage current in MOSFETs. Firstly, shrinking transistors growing problem. As transistors shrink to incredibly small dimensions, which is nanometers, the gate oxide, which insulates the gate from the conducting channel, becomes extremely thin, often just a few atoms thick. Next, quantum escapees. At such small scales, the wave-like nature of electrons takes center stage. They can tunnel through the thin gate oxide even if they don't have enough energy to overcome the barrier conventionally. As the gate leakage increases, this tunneling current through the gate oxide, known as a gate leakage, increases dramatically as the oxide thins, leading to the fourth point, wasted power. Leakage current represents a continuous drain on the battery even when the transistor is off, impacting battery life in portable devices. Heat generation. The flow of leakage current produces heat, potentially leading to overheating and reduced performance. Lastly, scaling limitations. Gate leakage poses a significant obstacle to further miniaturization. There's a limit to how thin the gate oxide can become before leakage becomes uncontrollable. Now let's dive more into this topic. I will introduce the tunnel field effect transistor, or known as TFETs. Tunnel field effect transistors represent a novel approach to transistor design aimed at overcoming the limitations of conventional MOSFETs, particularly in terms of leakage currents and scalability. TFETs operate based on the principle of quantum tunneling, which allows electrons to pass through barriers that would otherwise block their movement under classical physics. TFETs use a PIN or NIP structure where the middle part I has an equal number of electrons and holes, making it highly resistive. By applying a voltage to the gate, it can adjust the energy levels to open a tunneling window, allowing electrons to tunnel from the source to the drain. TFETs can switch states with a smaller voltage change, reducing power consumption. They also have the potential for better scalability and lower leakage currents. The materials used in MOSFETs like silicon and germanium are not ideal for TFETs because they don't support efficient tunneling. However, materials with direct band gaps show better performance in TFETs. Now let's see the similarities and differences between TFETs and traditional FETs. As you can see in the figure, both has the basic structure. Both TFETs and MOSFETs consist of a source, drain, and gate. The gate controls the conductivity between the source and drain by applying a voltage. There are four differences between them. Firstly, the control mechanism. The control mechanism accounts for the majority of the differences. MOSFETs modify a potential barriers with using a gate voltage, enabling carriers to pass over it. Conversely, using quantum tunneling, TFETs maintain a high barrier and regulate current by varying the likelihood that electrons will tunnel through it. Secondly, energy band diagram. The energy band diagrams of MOSFETs and TFETs in their on and off states illustrates the fundamental difference between the thermal injection mechanism in MOSFETs and band-to-band tunneling in TFETs. This distinction is crucial for understanding the operating principles and performance characteristics of each device type. The third is performance and scalability. TFETs are made to reduce leakage currents, enable voltage scaling, and counteract short channel effects. Nevertheless, because of the cross-sectional area that might be tunneled and the likelihood of tunneling, they frequently experience lower on currents than MOSFETs. This distinction affects both their overall effectiveness and applicability. Lastly, integration and compatibility. Some TFET architectures, like line TFETs, are designed to be CMOS compatible and easy to integrate using standard CMOS unit process steps. This compatibility is essential for transitioning from traditional MOSFET-based technologies to TFETs in a gradual and seamless manner. In summary, while TFETs and MOSFETs share a similar basic structure, their operation and performance are fundamentally different due to the underlying mechanisms controlling current flow. TFETs offer unique advantages, such as lower leakage currents and potential for further scaling, but also face challenges related to their own current and overall efficiency compared to established MOSFET technologies. Thank you.
So for the next point, it is technological implication and innovation in quantum tunneling. I choose in semiconductor and transistor. The implication is on tunnel diodes. These are type of diode that utilize quantum tunneling to achieve fast switching speed. They are used in high speed and microwave application. So for the innovation in quantum dots, there are semiconductor particles that exploit quantum tunneling for application in quantum computing and advanced display. So next, second, quantum computing, the qubits, the basics units of quantum computer use quantum tunneling, and superconducting qubits rely on the tunneling. Point number 3, tunneling field effect transistor. So it is about low power electronics. Tunneling field effect transistor leverage quantum tunneling to reduce power consumption in electronic devices. So it's offering a path towards more energy efficient technologies. And the fourth one is about advanced materials. Innovation in materials such as carbon nanotubes and graphene have led to development of resistor with improved performance characteristics such as lower noise and higher stability. The last point, the challenges and future generations of the implication and innovation. First one, coherence and noise. Maintaining quantum coherence and mitigating noise in quantum tunneling system is critical for reliable operation, particularly in quantum computing. Second one, material science. Developing materials that can efficiently harness and control quantum tunneling effects is an ongoing area of research. Novel materials like graphene and topological insulator should problems. And the fourth one, the last one, energy efficiency. Innovation aimed at reducing energy consumption through the use of quantum tunneling could have significant impacts on global energy use, particularly in data centers and mobile devices. In conclusion, quantum tunneling is not only a fascinating phenomenon from a theoretical perspective, but also driver of innovation across multiple technological domains. As research progress, the application and implications of quantum tunneling are likely to expand, leading to new and transformative technologies.
For conclusion, let's do a recap by answering some questions to test our knowledge after watching this video. So the first question is, what is quantum tunneling? Second, what is the example of quantum tunneling in nature and its technological application? Third, what is a transistor? Fourth, what is the relationship between quantum tunneling and transistor? And lastly, what are the implications and innovations that sparks from the application of quantum tunneling in transistor? That's it from us. Thank you.